This video illustrates the concept of perfect models as discussed in chapter 2 of the book. The dataset is shown here as a counts file. What was done that in 1942 the city of London was attacked by German bombs, and the London area was divided in 576 areas, and for each area it was counted how many bombs fell on that area. So the numbers go from 0 to 5 or more. After loading the data, the default choice in ILLMO is to approximate the data by a Gaussian distribution, which is shown here. So the red data, the red curve is the observed histogram. The green curve is the cumulative Gaussian distribution that is fitted to it, or equivalently, the red curve is just the regular observed distribution, and the green curve is the predictions based on the Gaussian model. Now, if the way the bombs fell on London would be random, then on theoretical grounds we would assume that the distribution would be Poisson rather than Gaussian. So we can check that by going to choosing a scaled Poisson distribution, and actually the distribution should not even be scaled, but we could just assume an unscaled distribution. So when we do that, we already observe visually that there's a much closer approximation between the red observed histogram and the green theoretical distribution, which you can show both here with the regular distribution but also with the cumulative distribution. We can verify that by asking for the maximum likelihood statistics, and by the way we can also see that the improved fit by the fact that the log likelihood criterion goes down, which is the black curve here. Another way to see that it goes down is to look at the data. So we see that for the original model the conclusion was that the chi-square with 3 degrees of freedom, which is the number of degrees of freedom in the data, which is 5, minus the number of degrees of freedom in the model, which would be 2 for a Gaussian model, because we have both an average and a standard deviation, that is larger than the threshold value, which would lead us to conclude that a Gaussian model doesn't, at least not perfectly, fit to the data. So the second model that we chose, which was the Poisson model, we get a much lower value, and we even obtain that with a model which has only one parameter. So here we see that we can accept this to be a perfect